Hello everyone. So in the last video we classified signals on the basis of their independent variable, that is a time. We also defined signal, how we will be using the mathematical definition of the signal for our future analysis. Now as far as the classification on the basis of time was concerned, we discussed continuous time signal, we discussed discrete time signal, we also discussed with your graphical representations and the subcases that can arise from the what you call from these two broad classifications, right? Now one thing you'll remember that when it comes to the real world, the signals that are generated in the real world from different sources, we don't have a real world source, that is a real world process, a real world phenomenon that generates a discrete time signal, right? You may take different phenomena, some natural phenomena like earthquake, it kind of generates a seismic wave which is purely continuous in time. Similarly, if there's a loud blast, yeah, you take any process, take any chemical process, take any biological process, the signals that are generated, they are continuous in time, right? So you won't have the exact discrete time. There is a definition, there is a discrete definition how we define a discrete time signal. But I'm talking about the physical significance. As far as the real world phenomena are concerned, we don't have a phenomenon or a source that typically generates a discrete time signal, right? Then there may be a question, then why do we then define a discrete time signal, right? So in due course of time, once we go through this course and the higher courses, you'll come to know that why there is a need to define discrete time signal, although we don't have a real world phenomenon which generates this kind of a signal. So what I'm trying to say here is that your real world processes, they always generate a continuous time signal. And your discrete time signal is actually derived from a continuous time signal, right? So the definition that we used here for discrete time signal is perfectly all right. But if you consider from an application point of view, when you consider the actual processes that are happening in the world, we may define discrete time signal as a derived version of a continuous time signal, wherein the time parameter has been discretized. And there are basically some processes that we do on continuous time signals to get a digital signal. Now we don't need to deeply analyze those processes right now, but just because we have done this classification, and we will just quickly through what the processes are. So you have a real time phenomenon, we have a real world process, and it will always generate a continuous time signal, that is x of t. And the first step we do on this x of t is we sample it, right? So we call this process as sampling. And after sampling, so this thing sampling, it will discretize time. That is, time will no longer be continuous, it will be in terms of discrete instants, right? So after sampling, I will be getting x of n. Then I do another process, what we call quantization. Like I said, we will be discussing them in detail, but I just want you people to know what the actual process is. The basis being that we don't have a physical phenomenon that actually generates a discrete time signal. So it's actually a derived form which we have derived from the continuous time signal. And quantization, this process discretizes the amplitude. So it kind of puts a limit on the amplitude. Then we have another small process, the process of encoding. And then we get what's known as a digital signal. So we start with continuous amplitude, continuous time, we do sampling. How it is done, what is the logic behind it, what are the physical laws that govern sampling. I'm not interested in that. You will learn those gradually, you will learn those. But what we get here is a signal which is continuous in amplitude but discretized in time. Then once we do quantization of this signal, we get discrete amplitude, discrete time. Then we perform encoding and you get a digital signal. And again, the question is that why do we do this process? If there is no general physical phenomenon which generates discrete time, why do we need this? This is something related to processing. And it is much easier to process in the discrete domain than in the continuous domain. That's a separate topic of discussion, but at least you should know what the flow is, what are our physical signals, the way they are generated, and how they can be converted from one type to another type. Right? So this here is continuous amplitude, continuous time. Once you do the sampling, so this is something that you will be getting after the process of sampling. Fine. And then once you do quantization, so you will get this. Then you can use some sort of signal form encoding and you will convert this into a digital signal. So this is a kind of relationship that these waveforms share with each other. Anyways, this was thoda sa reh gaya tha last lecture mein. Today we will be doing another classification. Like I said कि classification का कुछ context होना चाहिए. There should be some context on which you can classify signals. Previous classification was based on their type, the independent variable, and the next classification will be based on symmetry, the symmetry of signals. And on this basis we can either have an even signal and we may either have an odd signal. Right? We can quickly define them. So, and this classification you can apply to both continuous time case, discrete time case. For example, if I have a continuous time signal which we represent by x of t, it is said to be an even signal if it satisfies this relationship, that if x of t is equivalent to x of minus t for all t. But you can use the same definition for the discrete case, just you have to change the notation. X of n is equivalent to x of minus n for all the sample values, where you define the sample values n. Fine. And it is said to be odd, so this is the definition for even. And for odd, a continuous time signal x of t is said to be an odd signal if x of minus t is equal to minus x of t for all t. And you can generalize for the discrete time case, x of minus n is minus x times n, not x times n, sorry, x of n, like this. Okay. So if I have to show it in the form of a waveform, I will draw small waveforms here. So say something like this. This is symmetric. So this will be an even signal, because if you fold it around this axis, if you fold it, it will completely, it will be symmetric in the sense that it will completely overlap the other half of the signal. So this right here is an example of even signal. Okay. And odd signal, it will be anti-symmetric, say something like this. Fine. X of t, this is my time, so this will be an odd signal. Similarly, you have your sine and cosine waves. Your cosine, it's a symmetric signal, it's an even signal, and your sine, it's an odd signal. So this is as far as the classification is, or classification goes, the even and odd. But related to this, we will do a bit of mathematical analysis. Actually, there is a generalization that any signal, say we take the continuous time case x of t, which will very well apply to the discrete case also. So any signal, it can be expressed as a sum of even and odd signals. Fine. That is to say that every signal, it can be expressed as sum of two signals. One of these signals will be odd, another will be even. So if I put it in a mathematical sense, so it means I have a signal x of t. It will have an even component, let's call it x subscript e, and it will have an odd component, let's call it x subscript o. Fine. Let's call it 1, equation 1. If I do a small substitution here, that I will put t equivalent to minus t in this equation, what I'll get is x of minus t is equivalent to x of e minus t plus x odd minus t. But we just discussed that the even signal, it has a property that if my signal is even, then x of minus t will be equivalent to x of t. Now since this is the even component, so I can substitute that it is the same as x e of t, because it is even. And for this I will use minus times x naught t. Again, it follows from this property, even and odd. Okay, so let's call it 2. Fine. And if I add these two equations, if I add 1 and 2, what I'll get is x of t plus x of minus t is equal to x even t plus x odd t plus again x even t minus x odd t. So this and this will cancel, so I will get something like this, that is the even component of a signal x of t is actually equivalent to 1 by 2 x of t plus x of minus t, once you simplify this. Fine. So the even component is just the average of the two signals. Now there are two signals involved. Mathematically, it is x of t, one function, then we have x of minus t. But physically, they are related by an operation. We'll come to that. First, let me complete the analysis. So we have done adding 1 and 2. Similarly, we will do a similar operation wherein I will subtract second equation from the first one. So it will be x of t minus x of minus t, and on the right hand side I will have x even t plus x odd t minus x even t plus x odd t. Again, I will have some parts cancel, this and this will go. So what I'll get is, after doing a brief rearranging, that x odd is equivalent to 1/2 of x of t minus x of minus t. Right? So this is a pretty useful kind of equation. So whenever you have a signal x of t, it will have even component, it will have odd component. And if you want to find the even component, you take average of x of t. Yeah, you can sum up x of t and x of minus t by 2. Similarly, if you want to get the odd component, just do x of t minus x minus t. divide by 2, and you will get the odd component of that signal. Similar relations will exist for the discrete time case. Similarity is same. Now, just a bit of physical significance, because like I said at the beginning of this course, if we treat it as a pure mathematical course, it may kind of limit our understanding of the signals and systems. So just wherever I feel you can understand these things, I will just present a physical significance of these things. So the thing here is we'll be starting with the signal x of t. Just a second. X of t. Now to get an even component, to get an odd component, I need a similar signal x of minus t. Now mathematically it is simple substitution, t ke badle minus t use kijiye, that's it. But physically it basically represents a very important operation that we perform on signals. Fine. See, what effectively you are doing is you are changing the direction of your time axis. Simple example, just a second. If I have a signal x of t and it is defined for positive time t, like this, how should I define it? Say something like this. So this is x of t. Now if I perform some operation on it, which basically replaces t by minus t, what I'm trying to say here is I am changing the direction of my time axis. Substituting mathematically t by minus t, graphically it actually means you're doing something like this. So this will be my x of minus t. Let's try to compare these two waveforms. It is basically, like I said, it is a very basic signal operation. We call this folding. To be more specific, time folding. Replacing t by minus t mathematically means physically we are folding the signal. We will discuss it separately when we discuss the basic operation. So the thing is, you have a signal, you need to derive its even and odd components. What you do first, you have a signal, you derive its folded version. Then you add the original signal with the folded signal, divide by 2, that will give you even component. You have the original signal, subtract from this the folded signal, divide by 2, you will get the odd component. Fine. So this is the concept of symmetry, yet another very important classification of signals. Right? So stop here, further classifications will follow in upcoming lectures.